slide.
Should I start or do you want to stay a while? Okay.
Bonjour à tous, donc bienvenue à cette soutenance de thèse donc de Darius Mercadier, dont le jury est composé de Gilles Muller et Pierre-Évariste Dagan pour les encadrants de thèse, Kartik Bhargavan et Sandrine Blasi pour les rapporteurs, Caroline Collange, Xavier Leroy, Thomas Ornin et Damien Vergniaud, moi-même, pour les examinateurs, et donc j'ai été désigné pour présider ce jury. Donc Darius, tu as 45 minutes pour nous présenter tes travaux de thèse, et ensuite suivra la traditionnelle séance de questions.
So hello everyone and welcome to my PhD defense of my thesis, whose title was Usuba Optimizing Bitslicing Compiler, and which was done under the supervision of Pierre-Évariste Dagan and Gilles Muller. So first, what is cryptography? So whenever two people are talking through the internet, there is always a risk that somebody is listening to whatever they are saying. So in order to make their conversation private, they can encrypt it using an algorithm called a cipher, which will turn the conversation into a stream of random bytes, basically. Of course, cryptography is not limited to encrypting communications. You can encrypt banking data, databases, internet browsing, emails, hard drives, whatever piece of data you may think about, you can encrypt. So a very important requirement for cryptography is that your ciphers need to be fast. So whenever you are communicating with a server, like browsing the internet, for instance, you don't want to wait too long for your communication to be encrypted. Basically, you want it to be transparent from the perspective of the end user. And the pressure is even higher on the server, because in all likelihood there are many clients connected to the same server, all of which require encrypted data in parallel. And it's even more true nowadays with the Internet of Things and the whole lot of connected devices we have. So we all have smartphones that uses encrypted communications, and smartwatches, and plenty of other connected devices like CCTV cameras, for instance. And even when it's not about communications, well, if your computer has a hard drive that's encrypted, well, if you want to boot your computer, ideally you don't want that to take half a day, and it's better if it's fast. So one way to have fast ciphers is to use hardware implementations. However, that approach suffers from two drawbacks. So first, it's cipher specific, meaning that if for some reasons you want to use another cipher, well, you need a new hardware. And it's very final. If there is a vulnerability that is found in your implementation, well, you basically have to buy a new hardware or to stop using that algorithm. So instead, in this thesis, we are going to be interested in bitslicing, which is a technique to write software efficient implementations of ciphers. So because it's software, it can be applied to any ciphers. And once again, because it's software, if there is an issue with your implementation, you can always fix it, recompile it, and use the fixed variable. So what is bitslicing exactly? Well, the idea of bitslicing is to take the n-bit input of a cipher and to split it into 1 bit in n registers. So if we consider, for instance, a 3-bit input, we would need 3 registers to store it. Then there are some empty bits in the registers, and the key idea of bitslicing is to use those bits to store subsequent independent inputs. So if we consider some 4-bit registers, there are 3 empty bits, and we can thus store 3 inputs in the same fashion. And now, if we compute on those registers, we are actually computing multiple times in parallel the same operation. So if we do, for instance, XOR between the first and the third register, we are actually computing 4 XORs in parallel, and this is where the efficiency of bitslicing comes from. So basically, the wider your registers, the more parallelism you get. So in particular, modern CPUs offer SIMD extensions, which provide SSE registers, which are 128 bits wide, LX and LX2, which are 256 bits wide, and LX 512, which are 512 bits wide. So using those registers, you can compute your cipher 512 times in parallel. So however, the issue with bitslicing is that it's very hard to write bitsliced implementations by hand. So one of the reasons for that is that your n bits input of the ciphers becomes n variables, and usually n equals 64 or 128, so you end up dealing with hundreds of variables at any point of your program. So it's going to be not very readable and hard to write, and furthermore, C compilers are not really equipped to deal with such code and are pretty bad at optimizing them, meaning that if you want efficient bit-sliced implementations, you have to optimize them by hand, making the code even less readable. And well, if you think that readability is a matter of perspective, here are a few lines of code from a bit-sliced implementation of DES that I found online. So it's not me that generated it, and if you search on Google for a bit-sliced implementation of DES, this is basically what you end up with. Now, if there is an issue somewhere in the code, if you need to fix it or to change something, well, good luck with that. So, in order to write bit-sliced implementations that are high level and efficient as well, we designed the Usuba programming language, which I am now going to introduce over the example of the rectangle cipher. So rectangle is a cipher, and here you can see a pseudo-secret representation of that cipher. So it takes as input a plain text on 64 bits, so the input, and 25 keys on 64 bits as well. It then performs 25 rounds of computation, each of them XORing the plain text and the key and calling two subfunctions, so subcolon and shift rows. And it finally produces the cipher text. So the Usuba programming language is meant at, well, the Usuba implementation of that cipher is meant as being a straightforward translation of that circuit into some code. So we can find the input typed to be 64, which means 64 bits. And one first thing to notice is that since we are doing bit slicing, the 64-bit input is actually 64 independent variables, and that the Usuba language allows you to manipulate as just a single variable. Then we have the 25 rounds of computation, each calling XOR, each doing XOR between the state and the key, and calling subcolon and shift rows, and we finally get the cipher text. Another thing to notice is that the XOR between the state and the key is actually, since the state and the key are each 64 variables, it's actually expanded to 64 XORs by the compiler. Now let's zoom in on shift rows and subcolon. Well, first shift rows, it's a permutation from 64 bits to 64 bits. However, since we are doing bit slicing, each bit is in a different variable, meaning that this permutation can be written as 64 assignments. So fortunately, there is an optimization called copy propagation, which most C compilers already perform themselves, but you can also do it by hand. And the idea is that if you consider two instructions, the first one does an assignment, A equals B, and then you do something with the result of the assignment, so X equals F of A. Well, you can remove the assignments, and you end up with just X equals F of B, so basically the assignments can be performed at compile time. Well, the same thing can be applied to this permutation, to shift rows. So if you inline the function, then the compiler can remove all the assignments by copy propagation at compile time, meaning that shift rows is a permutation which is basically free thanks to bit slicing. So in Usuba, to write this permutation, we can take advantage of its underlying structure. So if we see the input as 4 times 16 bits rather than just 64 random bits, well, the first step of the permutation is an assignment from 16 bit to 16 bits. The next step is a left rotation by 1, then a left rotation by 12, and then by 13. So already Usuba provides some high-level abstractions to have a more concise implementation of that permutation. And then the Usuba compiler will expand the rotations to assignments and remove them through copy propagation. Then we have subcolon, the S-box of rectangle. So an S-box is basically a key component of most ciphers, and subcolon is a function, thus S-box, which takes 4 bits as input and returns 4 bits, and is specified using a lookup table. So basically, with the 4 bits of input, you index into a table which contains elements on 4 bits. However, cryptographic codes, well, lookup tables are vulnerable to cache timing attacks, meaning that your lookup table is stored in the memory of your computer, and whenever you do a lookup at an index, well, the table, well, the data at that index is moved from the memory to the caches, and then subsequent accesses at the same index will be faster because the table is in the cache rather than in the memory. And thus, an attacker can observe the pattern of your accesses to the cache and be able to guess at which index you are accessing the table, and thus what secret data you are encrypting. So instead, in cryptographic code, we prefer to use circuits to compute the hash boxes rather than lookup tables. So here, you have a circuit which takes 4 bits as input and returns 4 bits. It contains 12 logic gates which computes the subcolumn function. So in this thesis, we are interested in software rather than hardware. So this table will be written as a C function which contains 12 bitwise operations. Well, Usuba offers you a syntax to write this S-box as a table, and the compiler will automatically generate a circuit that computes this S-box. So there are 2 ways for that. Well, computing a circuit equivalent to a lookup table is a complicated task, so we reused existing results, which we incorporated into a database in our compiler. So basically, if the compiler of Usuba already knows your lookup table, it will provide with an efficient circuit from its database, and otherwise it will generate one using binary decision diagrams, which will not be as efficient, but is still enough to prototype your implementations, basically. So if we look at the whole cipher, it's pretty high level. It fits in one slide, and it's readable code. And then the Usuba compiler, Usubac, will compile it to C. And if we compare that implementation with the C implementations I mentioned earlier, well, Usuba provides abstractions that are much higher level than C, meaning that the bitsliced implementation is still a readable code, basically, and the C generated by the compiler is basically as efficient as Hentian implementations. Furthermore, well, Usuba is generic in the sense that the compiler can generate code for any CD extensions of Intel. So in particular, we can generate code for SSE, AVX, IVX 512, all of that from a single source implementation, and thus easily gain benefit from a nice speedup, thanks to parallelism. So all of that is pretty nice, except that there is an issue with bitslicing, which is speeding and register pressure. So if we consider, for instance, a 64-bit input, it's going to be transformed into 64 registers, well, rather 64 variables, except that your CPU only has up to 16 registers, which is much less than 64 variables, meaning that your variables are going to be stored in your memory, and whenever you need to compute with them, they will be fetched from the memory to the registers. You can compute with them then, and afterward, the result of the computation has to be stored in memory. So this phenomenon is called speeding, and it's showing, well, it's harming performance of bitsliced code. So to overcome this, there is a generalization of bitslicing called M-slicing, which we incorporated into Usuba, and which is declined into 2 slicing types, so vertical slicing and horizontal slicing. So I'm going to start by introducing vertical slicing on the example of chief rows from rectangle. So this time, the input of rectangle is seen as 4 times 16 bits rather than just 64 times 1 bit. And well, each of those 16 bits is put in different registers. And then if we consider SSE registers, for instance, there are some empty bits in the registers which we can use to store subsequent independent inputs in the same fashion as bitslicing. So here, we would be able to store 8 independent inputs. Then the question is, how do we compute on those data? Well, the first step of shift rows is a simple assignment, so basically nothing to do. Then you have a left rotation by 1. Well, SSE extensions offer instructions to perform left shift, right shift, and OR on 16-bit packed elements within SSE register, all at the same time. And with those 3 instructions, you can emulate a rotation. So basically, with those 3 instructions, you compute 8 rotations in parallel. The same goes for the left rotation by 12 and by 13. So overall, it means that in vertical slicing, shift rows requires 9 instructions, 3 per rotation. Well, compared to bitslicing, in bitslicing, shift rows was free thanks to copy propagation. However, it used 64 registers, 64 variables, and thus put a lot of pressures on the registers, whereas in vertical slicing, we only require 4 registers, and there is thus no need to spill any data to memory. The other declination of M slicing is called horizontal slicing, and this time the 16, well, it's very similar to vertical slicing, except that the 16 bits of the inputs are split, each of them in the different bytes of the registers. Once again, there are some empty bits in the registers, which we can use to store subsequent independent inputs. And once again, we can store 8 independent inputs in that fashion. So the first register will contain the first 16 bits of each input, each of them in a different byte. Question is, once again, how do we compute on those data? Well, SSC extensions offer shuffle instructions that perform an arbitrary byte shuffle of a register according to a pattern. So if you provide it with the right pattern, this shuffle acts as a left rotation by 1, by 12, or by 13. So compared to vertical slicing, shift rows is more efficient because you only need 3 instructions now, whereas in vertical slicing it was 9 instructions. So in that specific example, horizontal slicing would be faster than vertical slicing, but depending on your use case, one might be more efficient than the other. To summarize a bit the slicing types we can do in Usuba and how we do them in Usuba, well, slicing direction, so vertical, horizontal, or bit slicing, is controlled by the type system in Usuba. So if you want to bit slice your input, you use the type B64. If you want to slice it vertically, you use the type UV16x4, which stands for 4 16-bit variables sliced vertically. And if you want to slice it horizontally, you use the type UH16x4, which means 4 variables sliced horizontally. Now you may have noticed that the shift rows node of the rectangle is will have shown the same code for vertical, horizontal, and bit slicing. Well, for those nodes that can be sliced in any direction, Usuba provides a form of polymorphism. So basically, the type U16x4 contains an implicit polymorphic direction, which you can instantiate with any slicing direction, and it will change how the rotations are compiled. So if you specialize your node for vertical slicing, the rotations are compiled to shifts. If you specialize it for horizontal slicing, the rotations are compiled to shuffles. And if you want to bit slice your node, well, this time the directions is unimportant, because since you have only 1 bit in each register, well, vertical and horizontal slicing are the same. But this time, the rotations are compiled to variable renaming and are basically free. So this means that from a single implementation of rectangle, a single polymorphic implementation of rectangle in Usuba, type U16x4, we can generate many C implementations that can be vertically sliced, horizontally sliced, or bit sliced for many instruction sets. So if we compare the performance in cycle per byte, well, on general purpose registers, bit slicing is much more efficient than bit slicing, whereas on SIMD extensions, bit slicing is faster than those bit slicing and horizontal slicing. So here I'm showing in red the transposition. So basically, it's the cost of converting the data from their standard representation into the slice representation, and in blue the primitive, so that we just the core of rectangle. But in some settings, the transposition can be omitted if both the people encrypting and decrypting the data are using the same sliced algorithm. So it would be the case, for instance, if you are encrypting your hard drive, and in that case you can omit the transposition, and horizontal slicing for rectangle is faster than vertical slicing. So what it shows is that depending on your application and your architecture, one slicing might be more efficient than the other, and thus it's beneficial to have a high-level language which from a single implementation can generate many differently sliced implementations. So now that I've presented you the Usuba programming language, which offers high-level abstractions for bit-sliced and M-sliced cryptography, we are going to go into 3 different directions. So the first one is to generate efficient ciphers for high-end CPUs. The second one is to generate code for embedded CPUs that must withstand some side-channel attacks. And the third one, we are going to add a backend to Usuba for the Skiva CPU, which provides custom instructions for side-channel resilient cryptography. So first, we want to generate code for IM architectures with SIMD extensions. and we want to generate code that is going to encrypt a lot of data. So we consider that there are like many inputs that we can process, so we can fully utilize the CMD registers, for instance. And to do so, I'm going to present 3 optimizations that we do to generate efficient code. So the first optimization is a scheduling algorithm for bitsliced code, which aims at reducing register pressure. So most ciphers have a very similar structure. So each of their own take the state and the key as input, store them together, and then call the S boxes. So since we are doing bitslicing, the state and the key are many variables. So for the sake of simplicity, let's say that for the example, the state and the key are 16 bits each. So if we zoom in on the XOR with the key and the S box, well, the XOR with the key is actually 16 bitwise XORs. And well, the S boxes are usually small functions, taking typically 4 bits as inputs and returning 4 bits. And they are called multiple times so that the whole state goes through them. So if we look at when the operations are executed, well, first the 16 XORs are computed one after the other, and then the 4 S boxes are computed one after the other. It means that once we have computed the first 16 XORs, we have 16 temporary variables that are the input of the S boxes and that are alive at the same time, and this puts high pressure on the registers. So basically, most of them will have to be spilled to memory. So our scheduling algorithm will try to detect the XORs between the key and the state and the linear layer of the cipher, and to schedule them as late as possible right before the call to the S boxes. So in that case, it would reduce the amount of temporary variables that are alive from 16 to 4. So this is possible to do because, well, most ciphers have this very similar structure of XOR with the key followed by some S boxes, and this is what we exploit to perform this optimization. So if we look at the impact on performance of this optimization, so the black line is the baseline, and it's basically the performance of the Usubac code without that optimization, and the bars represent for many ciphers their performance when we activate this optimization. So if the bars are above the black line, this is optimization improves performance. Otherwise, it reduces performance. So in most cases, it improves performance from 5 to 20%. The next optimization is a scheduling algorithm for M-sliced code this time. And in M-sliced code, register pressure is not really an issue because we only use a handful of registers typically. However, what we want to do is to maximize the instruction level parallelism. So your CPUs are super scalar, meaning that they can execute multiple instructions per cycle, typically 4 bitwise instructions. And we just want to maximize the amount of instructions that are executed each cycle. So if we consider a simple example, a node which contains a for loop, which does a NOT and a XOR, but the XOR uses the result of the NOT, well, the bitwise NOT and the XOR cannot be computed during the same cycle because there is a dependency between them. So in that case, this code would execute in 8 cycles, and there would be no instruction level parallelism at all. So what our algorithm do is that we will unroll the loop, and then the operations with no dependencies would be scheduled together and can thus be executed during the same cycle. So here, the 4 NOTs would be scheduled first and can be computed in a single cycle, and then the 4 XORs are scheduled together and can be executed in the same cycle. So overall, it will reduce the execution time of that node from 8 cycles to 2 cycles. So you may expect most C compilers to already perform that kind of optimizations, or you may expect that the out-of-order nature of your CPU would alleviate the issue, but our benchmarks show that it's not the case. And on the ACE cipher, for instance, we gain a 35% speed up thanks to this optimization, and on a few other ciphers, we gain speed up from 5 to 10%, which for cryptographic implementations is already quite significant. The final optimization is an interleaving algorithm, which once again aims at maximizing instruction level parallelism in M-sliced ciphers. So this time we consider, as our example, a node which performs 3 XORs with a dependency between each of them. It means that they cannot be executed during the same cycle, and no matter how we schedule them, this node will always execute in at least 3 cycles. So in that case, what we do is that we interleave a second instance of the cipher with its own inputs and its own variables, with no dependency with that first instance, and thus that can be computed during, well, at the same time. So basically, in 3 cycles, instead of computing that node once, we can compute it twice. So once again, this is possible because we consider that we generate code for high-end CPU that must encrypt large amount of data in parallel, and we thus can always pull the next input to encrypt it alongside the current one. Once again, if we look at the impact on performance, on a few ciphers, it improves performance from 20 to 30%, which is very, very significant. However, on some other ciphers, it actually reduces performance, and those are ciphers which already have a very high instruction level parallelism, and thus do not benefit from interleaving. And furthermore, some of them have a very high register pressure, meaning that if we interleave a second instance of the cipher, well, it's going to introduce spilling, which is going to slow them down. So fortunately, we are in a setting where we do only sliced implementations, and sliced code is constant time by construction. So basically, within bitsliced or msliced code, there are no conditionals that depend on secret data, and it means that if you benchmark the execution time of the cipher for a single input, it actually gives you the execution time of the cipher for any input. And this is exactly what the auto-tuner of Usuba does. So basically, this tool, before committing to an optimization, Usuba, the compiler, benchmarks the impact on performance of this optimization on just a single input. And if it improves performance, we keep the optimization, otherwise we just discard it, we don't apply it. So overall, interleaving can thus improve performance from 20 to 40%, or just be neutral and will never be detrimental to performance. So we can now have a look at the performance of the implementations generated by Usubac compared to handwritten and hand-optimized implementations. So the black line represents the performance of the hand-tuned implementations, and the bars represent the performance of the Usuba implementations for several ciphers and several architectures. If the bar is above the black line, then Usuba is faster than the handwritten implementations, and otherwise Usuba is slower. So in the case of AES, the reference implementations are written in assembly and carefully optimized by hand, and Usuba is 3 to 5% slower. So that's due to 2 factors. So first, the C compiler, well, we generate C code, and the C compiler introduces some spilling in the assembly, whereas the hand-tuned optimizations do not contain any spilling. And furthermore, the hand-tuned optimizations fuse the cryptographic runtime with a primitive, which enables them to perform some additional optimizations, which we cannot do in Usuba. Then on Shasha20 and Serpent, the reference implementations are written in assembly as well, and hand-tuned and optimized as well. However, despite generating C, we are able to match the performance. And finally, on quite a few other ciphers where the reference implementations are written in C, we are able to quite largely outperform them, mostly thanks to our interleaving and scheduling algorithms. Furthermore, Usuba can always generate code for larger CD extensions, so we can always generate code for LX 512 and thus benefit from a very easy speedup. So in this section, I've shown you that thanks to a few, but I've shown you 3 domain-specific optimizations, namely 2 scheduling algorithms and 1 interleaving algorithm, that enables us to generate codes that perform on par with hand-tuned implementations, and which scales with CD extensions, and this was published at PLDI 2019. So in the next section, we're going to be interested in generating code for embedded devices, and those codes must withstand power-based station attacks that I'm going to define in the next slide. So this was done in collaboration with Raphael Wintersdorf, Sonia Belaid, and Mathieu Rivin from Crypto Experts. So first, what is a power station attacks? Well, we consider that the attacker has a physical access to the device, and then he can monitor the power consumption or the electromagnetic radiation of your computations, and is able to correlate that power consumption with what secret data you are encrypting. So one intuition for that is consider, for instance, an addition between two numbers. Well, it's easy to imagine that the power consumption of the addition might not be the same if one operand is 0 or if both operands are non-zero. To model this attacker, we are going to use the probing model, where we consider an attacker that can place T probes on the computation. So it can place T probes on intermediate results of your computation and thus gain knowledge about T intermediate results. If T is greater than 1, this is called a higher order power analysis. And to protect against those attacks, we are going to use a technique called Boolean masking, where each secret bit is represented as n random bits called shares, such that the source of those n random bits is equal to the secret bits. If n is greater than 1, then this is called higher order Boolean masking. And now, if an attacker can place T probes on your circuit, and if T is less than n, then it will not gain any knowledge about your secret data. So if you want to mask your whole circuit, you need to just replace its inputs with sharings and replace its operators with masked versions of those operators called gadgets. So in the case of a XOR, a masked gadget simply performs the sharewise XORs. In the case of a NOT, it's sufficient to just negate a single share. And in the case of an AND, well, the gadget is a bit more complicated, so let's just say that it's a black box. Well, however, it's not quite sufficient to just replace each operator with a masked gadget if you want to obtain a secure secret. So consider those few lines of code where we consider an attacker that can probe X, Y, or Z. So we want to make sure that X, Y, and Z are random. And initially, A and B are your secret variables, and R1 is a random variable. So X and Y are indeed random because they are XORed with a random variable. However, when you look at Z, equals Y XOR R1, and if you expand the definition of Y, you end up with Z equals A XOR R1 XOR B XOR R1, and both XOR R1 cancel out, and thus you end up with Z equals A XOR B. And since A and B are secret, if the attacker probes Z, it will gain information about both A and B. So in that case, what we would need to do is to add a new random variable, R2 for instance, and XOR it before getting the result of Z, and this operation is called a refresh. So it's a very complicated task to know, given a circuit, what to insert refreshers. So people that I mentioned earlier from Crypto Expert developed a tool called TypeProof Plus, which, given a mask implementation of a circuit, tells you where to insert refreshers. And in particular, it tells you what is the minimal amount of refreshers you need to insert. And this is very important because generating random variables is expensive, and you want to just minimize the amount of random variables you need in order to generate the most efficient implementations you can. So we extended the Usuba pipeline to generate masked implementation and to use TypeProof Plus to insert automatically refreshers. And we call this extension of Usuba Tornado, and I'm going to illustrate how this is done on a simple example. So we start with, as input, an Usuba program. And then the first step is a standard step of the Usuba pipeline called normalization, and we apply also some optimization. And we get down to a subset of Usuba called Usuba 0, where your code is basically, your nodes basically amount to low level, it's basically a low level language to describe circuits. So from there, it's very easy to generate code for TypeProof Plus, since the input of TypeProof Plus is very similar to Usuba 0, except that TypeProof Plus does not accept loops and functions. So at that stage, we unroll loops and inline functions. Then TypeProof Plus will insert refreshers if your code needs additional refreshers, and we will decode the output of TypeProof Plus back to Usuba 0 node with additional refreshers. And also at that stage, we rebuild loops and functions. Then to actually mask the code, we replace each variable with an array of shares and each operator with a masked gadget. So in the case of linear operators, you mask gadgets, so a linear operator that is left rotations, rotations, shift, and XOR. The masked gadget is a for loop, which iterates over each share and performs the operator. And in the case of the AND and refresh, we'll leave the mask gadget as a primitive call which will be linked with assembly later in the pipeline. So right now, well, at that stage, there are a lot of loops in the code which will slow down the computation if we'll let the code as is. So before generating C, we have a path of optimization which, among other things, perform loop fusion. So we merge loops together whenever we can. Once again, this is an optimization that most C compilers already perform. However, we are more aggressive in Usuba, and we are thus 10 to 15% faster by doing so ourselves, and we can then generate C and assembly using GCC. So in this section, I've shown you the tornado extension of Usuba, which automatically performs Boolean masking and uses type2+ to insert refreshers, while just to generate implementations that are probably secure to power analysis, because type2+ gives you a security proof. We were able to generate mask implementations at very high masking order, so up to 128, meaning that you would need 128 probes to break them, which would be, well, quite prohibitively expensive. And using this extension of Usuba, we compared the performance of 11 ciphers from an ongoing competition of the NIST to find a new standard for lightweight cryptography. So this allowed us to bring new insights into the competition and into the trade-offs of each ciphers, especially when you mask them. This was published at Eurocrypt 2020. So finally, we added a backend in Usuba for Skiva, which is a custom CPU providing instructions to protect against many sidechain attacks that I'm going to introduce in the next slide as well. So this work was done in collaboration with Pantea Patrick Chaumont from Worcestershire Institute, and Karin Heidemann from Lipsix. So in this setting, we consider an attacker that can do timing attacks, so basically monitor the execution time of your program to guess what secret data you are encrypting. He can do for analysis, so the same as in the previous section, but he can also inject faults in the computation. So basically what he will do is that he will for instance, well, inject faults, for instance, by blasting some ionizing radiation using a laser on your chip at a chosen time and a chosen location. And it will observe how this fault impacts the result of your computation, and thus deduce what data you are encrypting. So first, we consider that you can introduce faults onto data. So basically, you can set a register to 0, flip a bit, flip a byte, or something like that. But you can also inject faults on the control flow. So basically, skip an instruction or change an instruction. So we are going to use several countermeasures to protect against those attacks, and we will combine them thanks to bitslicing and thanks to the aggregated bitsliced model that I'm going to introduce now. Well, first, timing attacks are not an issue in that settings because we use bitslicing, which is, as I mentioned earlier, constant time back construction. So the execution time of a bitsliced program is the same for all inputs. There are no timing attacks possible. Then to protect against data faults, we are going to duplicate each bit. So in our bitsliced register, instead of having 32 independent bits, we're going to keep only half of those, so 16 bits, and duplicate them. Now if there is a fault and one of the bits is corrupted, we'll still have a valid copy. If we are worried that there might be 2 faults, well, we can always keep 4 copies of each bit, and now we are secure against up to 3 faults. Then to protect against power analysis, we're going to use Boolean masking, so the same thing as in the previous section, and thus keep only half of the bit and represent 2 logical bits with 2 random bits, such that the XOR is equal to the secret bit. So I'm going to keep just 1 square per logical bits rather than physical bits. So each square here represents 2 physical bits. If we are worried that the attacker may perform power analysis at a higher level, well, we can always keep half of the bits and use 4 shares per bit instead of 2. And finally, to be secure against control faults, well, we are going to keep only a single bit. And in the registers, store the output of round n and the output of round n-1 for that bit. And since each round is identical in a cipher, when we compute a round on that register, we get the output of round n and the output of round n-1, n+1, meaning that we computed twice the output of round n at different time, and we can compare the two. So the Skiva custom CPU provides instructions to efficiently generate redundant data, to check that redundant data are correct, meaning that, well, it's actually redundant and no fault was injected, to compute on redundant data, to generate masked data, and to compute on masked data. And we added a backend in Usuba to generate code that can run on the Skiva CPU. And we are thus able to generate implementations that are secure against timing attacks, fault on the data, fault on the control flow, and power analysis. And this was published at COSAD 2020. So to conclude, in this thesis, I've developed the Usuba programming language, which offers high-level constructions for symmetric cryptography, and which performs automatically bitslicing and mslicing. In the first axis, we developed several optimizations to generate IN code for efficient implementations for IN CPUs. And we showed that starting from a high-level language, we can generate implementations on IN CPUs that are as efficient as Antium implementations. We also showed that this is only made possible thanks to the optimization we perform that would not be possible in a traditional C compiler. So for instance, our scheduling algorithm for bit-size code takes advantage of the structure of ciphers to perform the XORs with the key right before the S boxes. Or when we perform interleaving, we take advantage of the fact that we are encrypting a large amount of data, and thus we can always encrypt more in parallel, which would not be possible without a domain-specific language. Then we extended the Usuba pipeline to generate mask implementations for embedded CPUs, thus showing that despite the fact that Usuba is high level, it's possible to use it to implement very low-level countermeasures against power analysis. And finally, we added a backend for Skiva in Usuba, thus enabling the use of Usuba to write code for this very specific platform. So as far as perspective and future work is concerned, well, our slicing model, so bit slicing, horizontal slicing, and vertical slicing, is somewhat limited, and well, there are some intermediate between vertical and horizontal slicing that enables faster implementations with the same property as M slicing, meaning you can encrypt in parallel and you are constant time, and it will be beneficial to add that to Usuba. Then there is a question also of what to do when there is no parallelism. So right now, our efficiency comes from parallelism. We can always encrypt many inputs in parallel, but in some settings, you just want to encrypt a single input. And well, in those cases, some people, what they do is to slice only within the cipher instead of slicing over many inputs. And it's useful for some use cases, and it could be useful to incorporate that in Usuba. So right now in Usuba, we only describe the primitive. And if you want to encrypt a large chunk of data, you need to call the primitive multiple times, and you need to chain the calls to the primitive using a mode of operation, which currently you cannot describe in Usuba. However, by incorporating that in Usuba, it would enable some additional optimizations. Then in addition to Skiva, we could target some other platforms. So there are some other custom CPUs for cryptography, for RISC-V, for instance, but we could also think of generating a hardware implementation directly, or well, think about the possibility to know that we have a high-level language for cryptography. Then what I've showed you for high-end CPUs, well, the optimizations rely on the microarchitecture of the CPUs, and the question is, how does that apply to other architectures? So on ARM, where you have the Neon extensions, or on GPUs, which are parallel by nature, and that's a good target for bit slicing. But maybe generating code from Usuba to GPUs might be trickier than just for general purpose CPU. And finally, for embedded CPUs, so in the first axis of the thesis, when we generated code for IN CPUs, we showed that it's possible to start from a high-level language and to generate code for IN CPUs that is as efficient as Antium implementations. However, for embedded CPUs, the code generated by Usuba lags behind handwritten implementations, and it's slower by about 1.8 times. So the question is, can we do better? And it would seem that if we want to match the performance of handwritten implementations on embedded CPUs, we need to generate assembly directly. However, it's not clear if that would be enough or not. So maybe the conclusion is that, well, we need to, it would be interesting to know if it's possible to generate implementations on embedded CPUs that can match the performance of handwritten implementations. Thank you. I'm done.
Thank you. Okay, thank you. So we will now move on to the Q&A session. So as usual, we will start with the reviewers. So Sandrine, can you hear me?
Feedback visuel sur le...
Yes.
So can you start, please?
Can you hear me?
Yes.
We can hear you, but we cannot see you.
Ah. Okay.
No, we can.
It's good.
Okay, so first of all, I would like to thank Darius for the very nice presentation that highlighted the wide spectrum of his work. My first question will be about the optimizations. So, are there any possible conflict between the optimizations that were designed and those of existing compilers? And a related question is, how can you check that there is such a conflict?
So, yeah, good question. Well, I don't exactly know what you mean by conflict, but for instance, the scheduling we perform for initialized code, well, the C compilers are completely free to just undo our scheduling. And in some cases, that's what happened, and that explains why we are slower. Well, our scheduling algorithm is actually not efficient. Interleaving, however, I don't see any conflict. And for the scheduling, well, once again, the issue with scheduling is that since we perform scheduling at the level of the C, and that the C compiler is always free to completely ignore what we did and to completely undo that optimization. So, well, fortunately, it works well. But I wouldn't be surprised if at some point with a new version of Clang or GCC, our optimizations just become completely worthless. And maybe generating assembly would not have run into that issue yet. But since it works well enough with C, we are happy with that.
Okay, and a related question was how can you check that a given optimization does not interfere with existing ones?
So, well, basically when I developed the optimizations, I checked by hand what was happening in the assembly and stuff like that. Now, when it comes to the code we generate with Usuba, I would say that we don't really care whether the optimization conflicts with the C compiler or not, because the autotuner will not let Usuba perform an optimization that reduces performance. So it could be interesting maybe to just have some more feedback in the compiler to let you know that the optimization was not efficient. But yeah.
Okay, thank you. I have another question about interleaving.
Yeah.
So you told us that you perform an interleaving pass in order to improve the performance, but I was wondering if this is a good practice that cryptographers are used to follow.
It is, because I found some, well, I mean, I guess it is because I found a few implementations written by well-known cryptographers that use this technique. To my mind comes the serpent implementations, for instance, the ones that are in the Linux kernel, they use interleaving. Then Gimli, which is a very recent cipher, written by some well-known cryptographers, including Daniel Bernstein, and the reference implementation uses interleaving as well. So I assumed it was okay to use interleaving.
Okay, so this interleaving was done by hand? By this
Yes, they did it by hand.
Okay. Yeah, in the manuscript you wrote that you have struggled to domesticate 3 different C compilers, and when I read the manuscript, I had a feeling that you sometimes had a hard life with these 3 compilers. So I would like to know what are the lessons you learned when struggling to domesticate this compiler, and what was the difficult task?
Well, the idea is that some optimizations are, so nice tricky question by the way. The idea is that some optimizations work well with some compilers and not at all with some other compilers. So I don't have the exact numbers in mind, but fortunately I can find them. Okay, great. So so that's the performance of the bit-size scheduling, but for each compiler. So in red, for instance, you have Clang with a compiler using option -03, and you can see that the interleaving is not efficient at all. Doesn't bring in the scheduling of bit-size code does not bring anything. However, if you compile for some other instruction set or with other compilers, well, it's crucial to the performance. And understanding why from one compiler to the other the optimization is not efficient is a bit complicated. And it's especially more important because some ciphers are only efficient with a given compiler. So for instance, if you compile our implementation of ShaSha20 with ICC, you end up with performance that are on par with hand-tuned implementations. But with Clang, we are about 10% slower than hand-tuned implementations, assembly implementations. So we need our optimizations to be efficient with each compiler, but they all have their own, in particular, instruction scheduler and register allocator. And well, that makes it complicated to generate optimizations that have a real impact for every compiler. So among the lessons learned, if I had to start again, maybe I would consider assembly as a target earlier in the stage, especially since the code we generate are fairly simple. We only use just a few instructions, like there are probably less than 10 operators, and we just need like 10 operators and memory instructions. So I would expect that maybe we should have considered assembly earlier than C. Oh. That's it.
Okay, thank you. Maybe a last question. Cryptos that could benefit from bitslicing. I was thinking, for instance, of program obfuscations, where there are some transformation that looks very similar to bitslicing? And
yeah. Are you finished? Are you finished with the question?
I think we missed the end of your question. Sorry, could you repeat your question, please? We couldn't hear.
yes. So maybe I will repeat my question.
Yeah, please.
So my question was, do you see another field than crypto that could benefit from bitslicing?
Oh, I mentioned that a bit in the manuscript. You probably read it. Well, I guess image processing comes to mind because when it's parallel, it uses SIMD extensions. Even though for bitslicing it might not be really a good idea because it uses multiplications which would not be efficient in bitslicing. I found some people using bitslicing to implement some arbitrary precision multiplications or or additions. Interestingly enough, they didn't provide any use case, just said that they could do it, and they did it. When it comes to code obfuscation, so interestingly enough, that's somewhat close to my postdoc that I'm going to do later, which is about, among other things, whiteboard cryptography. I'm not sure how strong of guarantees you can get with bitslicing, with just bitslicing your code and or transposing and changing the representation of your data and say, well, that's obfuscated. Maybe it could be part of something bigger. I haven't really thought about it, but maybe yes. And as for other applications, well, the funny thing with bitslicing is that some people use it for other applications, like to simulate hardware or to perform arithmetics and stuff like that. But they almost never explicitly say what the use case is. So I guess you can do other things with it. And the question is, do you want to do other things with it? Maybe the answer is no. I don't know. I'm done. I think we lost you.
Okay, thank you. So I'm done as well.
Okay, thank you, Sandrine. Thank you. So the second reviewer is Kartik. So you hear us? Yeah.
Yeah.
So please.
All right. So let me go. First of all, thanks for that. Was a very great talk, very clear and explained a lot of things. Of course, I also had the opportunity to read and review the thesis, and you can see from the review that I really loved it. It was one of the most enjoyable theses I've read in recent times. A good test of a thesis I find is also whether it helps other students. In fact, I gave a thesis to one of my students who works in a very related field, and she loved it. She enjoyed it from beginning to end, so you passed that test. I don't have too many questions because I think I understand the work quite well. But let me ask you a few. My first question is really about verification. You mentioned it in passing at the end of the thesis. The compiler significantly reduces the TCD for this kind of crypto code because now you only have to review the transformations under the compiler and don't have to review every single implementation. But even so, it would be nice to know that the code generated by Usuba is correct with respect to some high-level spec. So how would you imagine you could go forward trying to provide this kind of high assurance to the crypto code generated by Usuba?
First we experimented. So I can use some visual support for that. The semantics of Usuba is fairly simple, and it's fairly similar to other works that have already proved the correctness of the compiler. So in particular, there is a work proving the correctness of the Lustre compiler a few years ago. So we can reuse part of that to prove the correctness of the front end of the compiler. Then the backend, we experimented a bit with transition validation. So basically extracting equations from the Usuba code before and after the optimizations and making sure that they are equivalent. And it seems to be very efficient and to work well because basically the Usuba 0 code is very, very close to the input of the SMT solvers. So that works well. And then the code generation pass. Well, I guess the easiest is to piggyback on some existing work. So either ComSet, but it lacks SIMD extensions, or some of them at least, but I think most of them. Or Jasmin, which is an assembly language with a verified tool chain, and which already incorporates some SIMD extensions, so at least SSE, I think. And that's how we would have a completely verified tool chain, except that right now we rely quite heavily on the C compilers to produce efficient code. And if we do that, we would not have GCC or Clang anymore. And unfortunately, ComSert is somewhat slower. So if we want to do that, either we accept that there will be an impact on performance and we will be slower, or we need to implement some other implementations in Usuba directly. Maybe go through more intermediate representation, perform register allocation ourselves, or instruction scheduling. So yeah, if you want to keep the same performance as right now and provide assurance, it's going to be quite a lot of work, but I think it's doable.
Okay. Just a further question on the translation validation thing you just mentioned.
Yeah.
On the masked implementations and
so we didn't try that.
The code structure changes quite significantly.
Yeah, we didn't try that on the masked implementations.
But you think similar techniques could work there?
I don't see any major issue for why that shouldn't work. In particular, when using translation validation, what we found is that the complexity, well, the complexity of the translation, the validation, is at most linear in the code size. Well, at least, but linear in the code size, and not exponential or quadratic or anything like that. Meaning that, well, masking basically mostly increase code size, and well, that shouldn't be an issue with the verification. I'm not sure how randomness works with stat solvers and how we should represent that. I must say I haven't thought about the issue. Intuitively, I would expect that it's doable.
Okay. So the other thing about Usuba programming language design is that it's since it's domain specific, it chooses a very, very specific problem, which is basically block ciphers, right?
Yeah.
Which is a large class of programs, but still, even within crypto, it's kind of limited.
Yeah.
So what about say more algebraic or arithmetic constructions like Galois fields or prime field arithmetic, which also can benefit from, I think, some of the M-sliced, B-sliced techniques that you have here, like 11305, for example.
Yeah.
Have you thought about how you could adapt Usuba in the future to more algebraic and Boolean?
So not a lot actually. So first, like my background is not in cryptography or mathematics, so Galois fields are kind of obscure for me. But even though there are already some languages which target that kind of cryptography, so like KO and Prairie Fact and some other languages, I'm not exactly sure what Usuba would bring to the table in those cases. In particular, I think Fact, which is a very recent language, already provides high-level abstractions to perform those kinds of instructions, and it supports SIMD extensions, even though you have to write them by hand. So Usuba could be higher level than that. Well, the operations used in that kind of cryptography are compatible with Usuba right now, except that they usually add some kinds of conditionals, which we do not support right now. But I think that's basically what we would have to add to the language, and the input size of the Usuba cipher are fixed, which is not always be the case if we consider some larger class of cryptography. So I haven't given it much thought. I guess a higher level language for most of those applications could be nice. My impression, however, was that it's harder to optimize, and I've seen much more papers trying to optimize those kind of algorithms than papers trying to optimize block ciphers. So I think we've chosen the easy subdomain of cryptography, and that if we want to generate efficient code for Galois fields and stuff like that, elliptic curve and etc., it's going to be harder to optimize. I agree that a high-level language for that could be useful, and maybe Usuba could be that language.
No, I totally agree with the argument that the goal of Usuba and for compilers in general should be that easy things should be easy, so that people can focus on doing the hard things by hand.
Yeah.
But even in things like Polygon 3 or 5 and so on, you will find that a good chunk of the coding effort is actually exactly the kinds of things we did with Kafka and in Usuba. So that's stuff which may not be of interest to Usuba, but the other half is similar to what you've been doing. All right, so one last question. Okay, so this is about interleaving. I found it very interesting to read about the auto-tuning step and how you deal with interleavings of various kinds and try to find the best possible interleaving on a particular architecture and so on. There is also a notion, a more useful, generally useful notion of what's called stitching, where you take two functions, which are supposed to be called one after the other, and you stitch them together, which is basically a form of interleaving. But they're not really like two iterations of the same loop that you're stitching together. Well, they could be written like that, but often they are two fairly different functions that can be done in parallel, completely in parallel. And so you might be able to stitch them together. And it seemed to me that the kinds of optimizations that you've already built into Usuba and the kind of auto-tuning you've already built into Usuba can be more these kinds of optimizations where you have two programs, completely different functions that you want to run in parallel. And this has nothing to do with bitslicing, but you use the same techniques to figure out what's the most optimal way of parallelizing them, basically running them in an interleaved manner. Have you thought about this? Is it compatible with what you're already doing?
Yeah, so I've somewhat thought about it. So first, in Usuba, when we generate code for iron CPUs, we basically unroll everything and inline everything, and then the scheduling algorithm would end up doing the stitching, basically. However, I can easily imagine, and it's the case in some cases, unrolling is not that good, and inlining is not that good because it increases register pressure and code size, which for all kinds of reasons could be bad. So in those cases, yeah, it could be interesting to do this stitching. It reminds me of, so I showed the example of ACE, which benefits very heavily from our scheduling algorithm. And the reason is that ACE contains a loop with a lot of dependencies, and within this loop, it can only compute one instruction per cycle. And when we actually, and this loop is within another loop. So basically, within within a function, but which is called 3 times. So actually, the simplest way a human would optimize ACE is probably to perform interleaving or stitching. Well, in that case, it's the same function, but on the 3 function calls, rather than inlining the whole code and interleave all operations, etc. So it's not obvious that stitching could improve performance in general on block ciphers. I can imagine that in some situations it would, and if we want to expand the application of Usuba, it could indeed be useful to have some finer optimizations than just inlining everything, unrolling everything, and scheduling everything. So it could be useful.
Okay. Well, thank you. That's my questions.
Thank you.
And see the
Thank you.
ground back to the project.
So now we will continue with the rest of the committee. So starting with Thomas. Thomas, are you here?
Hello, I'm here.
We can hear you. I can hear you and see you.
Okay, so okay, first I wanted to ask a question about GPU, but you actually observed it in the conclusion. So, okay, it's gone. And okay, so it was a very nice presentation. I thank you for that. I thank you also for picking up things that I was doing 20 years ago and I had shamefully abandoned. So it's good that it actually turns out to do something good. And I've been writing some code for that. And one of the parts about bitslicing, especially with old things like this, is that when you're doing those things, it's all over the way. So this means that you get CBC encryption, and CBC encryption famously is not parallel.
Yeah.
That is, to encrypt a block, you need to process it fully to start encrypting the next block. So if you want a constant time CBC encryption for that, it's going to be painful if you are going the bitslicing mode. So I tried something which is like an internal bitslicing, which I do the S block things in bitslicing mode, and I found single block. So I split the S blocks, each S block into 4 sub boxes, each with 1 meter code. So I have 32 boxes to compute, and I have 32 bits. So I put that into a 32-bit register, and then I'm using the same circuits for all boxes. But they are not the same. I mean, they are completely different. They produce different output for the same input. So the difficulty here is to have different boxes, but somehow find a common circuit to evaluate the input. Right now I'm using the tree, and in fact I'm expanding the input with some extra bits. So the 6 inputs become 6 intakes for 6 layer of tree, and I have 64 inputs, each of 32 bits. So the question is, I'm doing this in ways to somehow merge different test boxes into a common circuit for that kind of job where you cannot do it parallel.
So first, well, I'm well aware of what you are talking about. So the second bullet point on the top right rectangle, like slicing without parallelism. I had exactly your implementations in mind, so I read them from Bare SSL. I read your implementations of the ES, and this is what I had in mind. However, I have not worked on optimizing circuits at all in this thesis. I've read some papers about it, and I've given it some thoughts, but I haven't had the time to actually look in depth at it. So I'm sorry, but I don't really have a convincing answer.
I would not say it's urgent because it's tough, and cryptographers are now moving out of that and more into more modern design where with parallelism. So another question which might be not so relevant, but it's mathematically speaking, it's interesting. Okay, so another one is that you are developing C code. That's a common pattern in all programming languages now, something which is fashionable. So that's a good idea, but it's common enough. Is that they integrate with LLVM, and so they more or less generate the internal documentation language of LLVM, so that they can have the backend with the register allocation and so on, but they can avoid the C syntax, basically. So, have you considered that?
So, yes, we have. But we came to the conclusion that it would not really bring anything, well, it would not offer any improvements compared to what we have right now. On the contrary, maybe like the C code we generate is generic. You can use it with any C compilers you like. And for some ciphers, we discovered that some, well, LLVM is not always the best C compilers. And in some cases, GCC is better. In some cases, ICC is better. So if we were to generate LLVM intermediate representation, we would have to use LLVM then, which would generate some worse implementation in some cases. And furthermore, well, in terms of optimization and what we do, it would not make things simpler, I think, and nor will it make things more efficient. So I don't really see any clear benefit from generating code for LLVM. Pierre, si tu peux.
Okay, just considering a comment, because otherwise you answered all my question. If you go to the embedded system mode and you want to generate exponentially, there are two interesting points. One is that the scripting method becomes very simple, because usually there's no latency to opcodes. On very small microcontroller like ARM Cortex M4 or M0, when you do a read from memory, you get the value right away, so you don't have to worry about not using the result immediately. On the other hand, all the registers, all the scaling is becoming very expensive, because memory accesses are much more expensive than operations. And they can't be made in parallel because it's not super scalar. So in that case, your main target will be to reduce as much as possible the speeding.
Yep.
And that's probably how you could make it fast enough, is by making the primary goal to reduce as much as possible the speeding to memory. So of course that is better for vertical scale. For this slice, this no, we don't use the term slice. Slice. Because then you have to register. So on the very low level, and it's already in the ARM Cortex M0 Plus, there are 8 registers. Basically, you can play with 8 registers. So it must fit in 8 registers. So any speeding is basically 2 cycles for reading and 2 cycles for writing, versus 1 cycle for each operation. So that's where the cost is moving the data around. So that code generation itself really is easy. That is, removing the C compiler from it will not be that hard. Okay, so that's just a comment, and I don't have anything more interesting or uninteresting to say.
Yeah, but just to expand on that, there is an interesting paper by Stoffelen and Schwab, I think, that works well. I think it's maybe all the AES you need on Cortex M, which in which they generate efficient implementation of AES for Cortex M devices, and they have their own register allocator for AES, which they show perform better than the C compiler, the C register allocator of the C compiler. So if we want to think about generating code for ARM devices and generating assembly, I think that's a good starting point, since they already did some of the preliminary work. Yeah.
Thank you. Thank you. So now, Caroline, can you hear me? Maybe.
Yes.
Can ask a question, please?
So first of all, I'd like to thank you, Darius, for the very nice presentation. So I enjoyed both the presentation and the document. So I thought I like in the document that I saw the next paragraph is answering my questions. So that's very nice flow. I also like the discussion on the optimization and the low-level programming, like how to trade off, how to trade ILP for register pressure, or using the fancy attending instructions, or optimizing for the different execution ports. So I have a few questions. So you compared implementation using GPRs and implementation using SLD registers.
Right.
But can we have both? Can you use both GPRs and SLD registers at the same time? And would it help?
Yeah, that's a very good question and a very good idea as well. It could definitely help. Well, more or less, but so for instance, there is only one port on the CPU that can perform shuffles for SIMD extensions. So whenever you cipher do shuffles, well, most of the time some ports are idle. So if you have a general purpose implementation running at the same time, that one could use the other ports to perform its operations. So that's one thing. Then for LX512, I think there is only one. So I think it depends on the exact microarchitecture, but I think you have only one port that can perform shifts as well, and maybe only one or two for bitwise instructions, which leaves some other ports unused, which we can use for general purpose registers. And well, for any SIMD actually, only 3 ports can be used for bitwise instructions and arithmetics, and there is a fourth one that can be used for general purpose registers. So interleaving both at the same time could improve performance, I think. And something else that could be useful is to interleave horizontal slicing with bitslicing, in particular because when the horizontal slicing is blocked by the shuffles, the vertical slicing can keep running it doesn't require shuffles. So good question. It probably could be interesting. Yeah.
And from an implementation perspective, currently you're using macros.
Yep.
So I guess you have to redesign that.
Just a bit, I think. The macros just say on right now. It would just need to say on SSE, and we are done basically, I think.
Okay.
And just write multiple instructions and yeah.
Another question, which you already partly answered, is what kind of new instructions you could benefit from using bitslicing? So you mentioned in the document the lookup table instructions of HX512.
Yeah.
Or the TR2 instruction scalar. But are there other instructions that you could imagine that would help?
So I don't have many examples in mind in particular because, well, bitsliced code and msliced code in general are very simple. So basically we need a XOR, an and an OR for bitwise code. And for msliced code we have some additions and multiplications as well, but it's fairly simple. So and well, it means that there are not a lot of room for optimizations. So yes, the ternary logic instruction of LX712 is clearly a very good one. For GPUs, there are some similar instructions as well, which could be useful to generate code for those instructions. Very similar to ternary logic instructions. But for on the general purpose CPUs, I don't see many room for people optimizations and that kind of things.
Okay. Even with M-slicing, for instance, like a long time ago in the Cray barn, you had a bit matrix multiply instruction, and that you have the same kind of instruction in the Calgary embedded processor.
Yeah.
So it takes 64-bit register and interprets them as 8 times 8 bits matrices of bits,
Yeah, okay.
and makes matrix multiplication. Could you use that kind of instruction?
I don't see any direct use, but maybe I should think more about it, but I don't really see.
Okay, fair enough. So that's it for my questions. Thank you.
Thank you.
So Xavier,
Yes, turning on my camera. Can you all hear me?
Yes.
Okay, very good. So Darius, well, first I wanted to congratulate you for this nice piece of work. Presentation was nice, and the PhD document is actually quite impressive concerning the breadth and depth of the work you did during your PhD. And well, maybe some of that is a little bit of my fault. Just a personal anecdote. But a few years ago, I was when I was talking to your colleagues in security and mentioning bitslicing as an example of a language/compiler technology that has relevant cryptography and security. And in the room there was a brilliant young research scientist called Darius Mercadier, and who then came to see me afterwards and said, "Oh, this is cool. Do I have your permission to work on this topic?" And I said, "Yes, of course." But so I'm really glad to see what came out of that, and what you've done goes much farther than everything I could have imagined at the time. So this is really great. Just saying stupid things in public and then seeing a great PhD thesis for you 5 years later. So I have a couple of questions. The first one is about the scheduling and register pressure issue. So that's your slide number 20. It's interesting that you run into, and not very surprising that you run into this problem, because I have seen it in many other contexts involving data flow languages, in particular just generating numerical code from Lust or state sheets in the avionics industry. Okay, and even there, there's enough possible parallelism in the DAG of computation that if you don't schedule cleverly, you end up spilling. And so I kind of like the heuristics you try to apply, but still I'm not sure how general they are. Basically, so it is very specific to the use of S-box. You're using your S-boxes as kind of hints of very strong scheduling hints, or is there a more general algorithm behind?
So right now it's very specific to ciphers that have S-boxes, in particular because I perform some inlining before the interleaving because, for instance, I need the source to be inlined if I want to interleave them right before the S-boxes, if they come from a function, for instance. And to perform that inlining, I inline basically all functions that are linear. So basically, with functions that contain only XORs and linear operations. And I don't inline functions that are non-linear, which are usually S-boxes. So for that inlining pass, I heavily rely on the property of the ciphers, on block ciphers. That is, they have some linear parts and non-linear parts. I experimented with some other heuristics before, inlining small function, inlining function that contains some amount of assignments. So it's possible to get similar results when we ignore the structure of the cipher, which works on my examples, but I'm not really sure it's very generic, and it's still cryptographic code. But yeah, this algorithm is quite specific to cryptographic code. Yeah.
All right. And so just to make sure, it's a different algorithm and a different path than the one that handles the other, the symmetrical issue that you have on slide 22, where here you want to schedule to increase instruction level parallelism and possibly register pressure.
Yeah.
So you're not trying to have some kind of unified scheduling, register pressure aware scheduling algorithm.
No.
Basically.
No.
Okay. Well, it's obviously a hard problem over BNP. I'm still hoping that there are good generic heuristics that we could put in your Usuba compiler, but also maybe in a Lustre compiler, for instance. Let's see. Yeah, so Karthik mentioned verification or possibilities for doing formal verification and building trust in the generated code. Very cool that when I see bitsliced code, like on your slide 5, it looks totally impossible to review. And I think, well, you and Karthik are right that you could do a lot with translation validation using SAT-solving, essentially. This said, so it reminded me of a discussion I had with another area cryptographer, Nicolas Andrier. I was telling him that symmetric ciphers are amazingly easy to test, okay? Because if you make even the slightest mistake, then you will not pass the test vectors, and you know that there is a mistake. I was claiming that it was essentially in the nature of those codes that it was impossible to get the correct result on test vectors by mistake. And he said, yes, for unintentional mistakes, but what about backdoors? Okay, intentional mistakes that will actually, once in a while, leak some secret data. And I was wondering, how could I get trust or confident that there are no backdoors in your generated implementations, either by formal methods, either by testing, is there anything that your approach offers here for the really paranoid user?
Well, my friendly face could be enough. If not
for the paranoid users.
So I haven't thought about it at all. I mean, the goal of Usuba is to have a language that is so high level that it's obviously correct, and well, extremely simple and obviously correct, and hopefully even someone somewhat paranoid would see the code and can like take even just in half an hour, you can be sure that there is no way that there is a backdoor. More than that, I've really not thought about it. Sorry.
Okay, food for thought. And maybe one last question. It's actually the follow-up to Caroline's question about mixing general purpose registers and SIMD registers. In my very limited experience with SIMD, this often is costly because transferring data between GPRs and SIMD registers is hard. It is costly, especially if you really want to build vectors or take them apart. And so I was thinking of two things. One is did you encounter issues with the cost of changing representations, basically? So you have several representations of your sets of bits, but the input, the clear text and the cipher text come at a fixed format, which is a stream of bytes. And so you also have conversion steps, and I was wondering how expensive these are, or whether it's just negligible. And the related question is, if you were to mix several representations in the same cipher, maybe start in M-sliced mode and then go to pure bit slice and then go to D-sliced mode, how expensive would it be to change those representations on the fly?
So about the cost of transposing the data, so I have some numbers in the manuscript. So the algorithms are basically in n log n. So the larger your registers, the less expensive it is to convert the data first, well, per bit or per byte. And it would be, well, I have the rectangle slide. That could be of some assistance to answer that. Yeah, so here we can see the cost of the transposition compared to the cost of the cipher. But keep in mind that it's very specific to rectangle. In particular, for horizontal slicing, the transposition is more expensive than it is, for instance, on AES. But usually, even with the transposition, bitslicing is faster than direct implementations without slicing. So it's kind of an issue, but not that much actually if you have large registers. Then about converting, changing representation on the fly. So I don't see many use cases. So it's comes back to what Thomas said earlier. So he wrote a DS implementation, and which is not really bit sliced, except that the S boxes are. So right before the S boxes, he bit slices. Well, he mixes the input. Well, he kind of bit slices the state of the DS, and then computes the S boxes, and then changes the representation. So it is useful in some cases, and in particular because it allows him to process only one input at a time and still be constant time. So there are some use cases, but converting from bit slicing to M slicing on the fly, it would be very expensive. So and thus I don't need any use cases. So of course, some operations are more efficient in bit slicing. You would like to bit slice your permutations, which should be free, and then M slice what could be better in M slicing, but I don't really see any use case because of the cost of that transposition.
Okay, yeah, that matches my intuitions.
Yeah.
So, yeah, well, I think I'm done with my questions. So, thank you.
Thank you.
Okay, thank you. So now we'll move on to the PhD advisors, starting with Gilles.
Okay, so Gilles français. Étant donné que je suis responsable administratif de cette thèse, je n'ai pas grand-chose à commenter et une question à poser. Par contre, je voudrais me féliciter, dire tout bien que je pense de Darius, qui pendant ces 3 bonnes années a vraiment été un étudiant très très agréable et a donné une très bonne ambiance dans le groupe de travail. Donc c'était vraiment un très grand plaisir de t'avoir dans l'équipe. Et je tiens à t'en remercier encore.
Merci.
Merci.
Yeah, so I actually have a quick question, but before that, I wanted to jump into to his story. So actually, Darius started his master physics. He did his master physics with me, and so he went to my office as a young master student. I was very shy and very respectful, and so the first thing I said to him was, we are going to go onto an adventure, a scientific adventure together. This is science, so I have absolutely no clue of what we are doing, what we are going to do. So you should, I'm going to say stupid things, and you should stop me, and you should don't let me say stupid things, and be very careful. I'm going to say stupid things. And boy, that was a big mistake. For 3.5 years, everything I said, he would say, no, this is not true, and we would debate hours on end about, should we do this, should we not do this? And and every meeting would end with Darius leaving my office and saying, "Nah, I don't think it's true. I will run the benchmarks and we'll come back to this later." And I mean, he did an amazing amount of work, always trying to prove me wrong, but that was great. Sometimes I actually was wrong. It happened quite a few times actually, but it was always great to have these sessions and to have this debate and make something out of it. So that was great, and that's actually related to my question, right? That's not me talking about history. We started this adventure with some rough idea of what we wanted to do, and we met problems. And we also met people, Patrick, Chaumont, and Pansea from Worcester, Raphael, Sonia, and Mathieu from Crypto Experts. These people also brought solutions, which brought us to somewhere else than what we thought we were going. I mean, we started with DES, so that means we started from way far back. If you were to start today to achieve what you did in your thesis, what would you do differently, and what would you keep, if anything, right?
So I guess I would keep the advisor, you.
Oh,
what a question.
Would it still be data flow, or would it be something else?
That's a great question. Data flow. So right now the language is somewhat data flow, well, mostly data flow. Except that ciphers are not really data flow. Cipher is actually imperative, and at first I think I let you convince me too easily that it was a good thing to have a data flow language. Looking back, I should have thought more than I did. And well, yeah, that's the one thing we should change. Yeah, so basically cipher is imperative, and having a data flow language to write ciphers is probably a very dubious idea at best. But we made it work, and it has some advantages when it comes to verification. So we did not do it, so we did not benefit from the nice side of that. But if you want to do translation validation, it's very easy with our data flow language. So at least there is that. So the next PhD student that was going to work on that will have an easy time because of our mistakes. So that's nice. Other than that, I must say I'm very happy with how things went. So. Well, it's always easy to look back and say we should have not tried too much in that direction and just do something else, but objectively speaking, I'm happy with the result.
Thanks.
Thanks. So I will conclude. So I still have a few questions, even if most of them are asked. So first of all, of course, I would like also to congratulate you for your work and for your presentation. I had a question on slide 35. So Kartik asked you whether your final implementation is correct. Xavier asked you whether there is no backdoor inside. But actually, my question is your final implementation secure? Because assuming the one that is output by type proof is secure, can you prove that your final implementation is secure?
So not right now. Well, so the code generated by type proof is secure, proof secure. However, because we link with, we generate C code, there is always, when you do masking, there is always a chance that your C compiler does something wrong with your shares. In particular, the order of the instructions is very important. That's why we use assembly gadgets rather than C gadget for the multiplication and the refresh, because there could be some issues with C gadget and the C compilers generate them. So I wouldn't say I'm 100% sure the result is secure. So I think if we want to be sure, 100% sure that the result is secure, we need to generate assembly ourselves, and we need to extend the pipeline to make it aware of masking and add some proof in the pipeline for masking to make sure that it's preserved throughout the optimizations. But yeah, the biggest issue is that the C compiler can do some things that could undo masking or be a threat. Yeah.
So you have shown us many performance comparison for many schemes. What was your use case for what kind of cipher do you, not cipher, sorry, what kind of mode of operation do you use and in which setting for those comparisons?
So depending on the, well, basically, I'm going to just load that slide. Ideally, I just use ECB, and I say I don't care about the mode of operation. Okay. In some cases, the reference implementations use CTR, and they fuse the runtime with the primitive, and it's all assembly, and basically I can't change it, so I implemented the CTR myself as well to compare with them. And but yeah, basically I consider that the mode of operation is outside of the scope of Usuba right now, and I ignore it. So okay. ECB, and if needed, CTR.
Because yeah, you mentioned several times that disk encryption is some target for instance. So I'm not sure. So hopefully ECB is not used for that.
Oh, no.
CTR maybe.
But counter.
It's not. So I think for disk encryption, the most what he uses is GCM.
Oh, yeah.
So it's there is some countermorph for the block cipher, but in addition there is this MAC that is computed, and so have you tried to see how it will?
I have not.
Okay. So I think that's interesting because so it's basically it's a counter mode, so you can use interleaving and all this kind of stuff, but still you have in addition to take into account the hash computation. I think that's something interesting. Yes. So you already had the question on the other applications of Usuba. So for instance, for cryptography, I'm not sure it's very useful for arithmetic in cryptography, in public key crypto, for instance, for elliptic curves or for, but maybe it's useful in crypto analysis. So if you want to solve discrete log on elliptic curves over a finite field of characteristic 2, and you want to perform parallel collision search, then in this case maybe that's useful. For cryptography, I'm not sure, but it was just a comment because it was already asked. And yeah, I was surprised in so for the last part of your talk with the Skiva. So when you presented this slide, so basically what you are using is some repetition code to avoid the fault attack, and then you are using secret sharing and the classical techniques. So I was wondering whether it's possible to actually use some different error correcting codes that will perform at the same time error correction and sharing and security against power analysis and this kind of stuff.
Can you, the question exactly is?
Yeah, because on this diagram you show us that before the first step is to use some repetition code, repeat, and then you use secret sharing.
Yeah, actually it's maybe a bad image, but we can do, well, we don't have to do sharing if we want to do control fault protection, or we don't have to do duplication to do sharing. Each of them are independent, and there is a quite large design space where we can do, at the same time, we can choose between 1, 2, or 4 shares for the masking, 1, 2, or 4 shares for the duplication, and 1 or 2 shares for, well, slices for the temporal redundancy for the control faults. So that's 18 possibilities, and we can do any of them. Okay, well, just one.
Thank you. So I will stop here for my questions, and so I think that's over. So we will now have the committee discussion. Thank you.
Thank you.
Thank you. So we will put on hold the YouTube channel. We'll be back in some time after the deliberation. So it will be muted and silent. It will come back live later, hopefully. I mean, if he becomes a doctor, right?
que tu as développé pour produire des implémentations optimisées et sécurisées de construction cryptographique par découpage binaire ou bitslicing. Au cours d'un exposé clair, dynamique et bien construit qui a mis en évidence tes qualités pédagogiques, tu nous as montré l'ampleur du travail d'implantation et de validation expérimentale que tu as réalisé pendant ces 3 années de thèse. Tu as illustré les résultats obtenus par des applications d'un excellent niveau dans un domaine de recherche d'actualité et d'importance, les implantations sécurisées contre des attaques par canaux auxiliaires et contre des attaques par faute. Lors des nombreuses questions soulevées par le jury, tu as démontré une très grande maîtrise technique ainsi qu'une aisance et une maturité scientifique. Dans tes réponses, tu as notamment démontré une grande connaissance de la cryptographie symétrique au-delà de ton sujet principal de recherche. Nous avons été impressionnés par la publication des résultats dans des conférences majeures de 2 domaines différents de l'informatique, donc PLDI 2019 en théorie des langages et compilations et Eurocrypt 2020 en sécurité et cryptographie. Et donc nous sommes convaincus que tu as toutes les qualités pour devenir un excellent chercheur ou enseignant-chercheur, et pour toutes ces raisons, nous te décernons le titre de docteur en informatique de Sorbonne Université.
Merci.
Bravo.
Du coup, je vais déjà remercier le jury d'avoir accepté de juryer cette thèse, de faire partie du jury. Et en particulier les rapporteurs, Kartik et Sandrine, dont les rapports étaient positifs et très agréables à lire. Et donc, merci d'avoir pris le temps de lire ces 200 pages qui ont dû faire peur au premier abord, j'espère, peut-être. Et à tout le jury en général. Ensuite, je vais aussi remercier Gilles et Pierre-Évariste. Et notamment Pierre-Évariste, je pense que je suis très content de ces 3 années et demie qu'on a passées ensemble. Et je pense avoir beaucoup appris, pas juste en termes de recherche, mais en termes de méthodologie de travail, etc. Et je pense être un membre bien plus productif de la société désormais. Non, mais je pense que je peux beaucoup plus facilement, j'ai pas beaucoup d'appréhension vis-à-vis de mon postdoc et de la suite. Et je pense que j'ai des méthodologies de travail que j'ai acquises notamment grâce à toi qui sont très solides. Et je pense que tu as fait du bon travail dans quel moment. Ensuite, je veux aussi remercier tous mes camarades doctorants et maîtres de conférence aussi, au passage. Notamment tout le bureau, Reda, Lucas, et les anciens, Antoine et Cédric, bien sûr, et Pierre aussi. Je t'ai pas oublié. Et ma famille aussi, bien sûr, qui a toujours su poser des questions auxquelles il ne comprendrait pas les réponses, c'est-à-dire la question sur ma thèse, et qui m'a beaucoup soutenu, et puis bien sûr Marjorie, d'être à mes côtés tous les jours. Et donc voilà, mais merci à tous d'avoir, notamment tous ceux qui ont écouté aussi cette thèse. Je pense qu'il y a, bon, en tout cas, il y a une bonne partie de ma famille qui a dû écouter, donc rien comprendre avec mes rêves. Du coup, vous tous qui êtes là depuis 2h30 sans rien comprendre, je vous applaudis, bravo, parce que c'est un bel effort que j'espère que j'aurai fait pour vous. Et donc merci à tous, et puis merci.
Bravo.
Il faut du enchaîner.